programming abstraction that are overlaid on top of disks to help applications and users store data and retrieve them. File systems exist because disks in reality are very low-level abstraction. So they view data as blocks. They don't really understand data as in, they just understand it as a sequence of bytes. They don't understand users, so they cannot protect things like files, whereas in reality systems consist of multiple files, processes create different kinds of files, multiple threads may access the same file. There are a whole bunch of programming or higher level issues that need to be dealt with that disk level, disk drivers scheduling cannot. Data might be also corrupted if the machine crashes, and file systems need to deal with this. File system model essentially is a unit of storage, treats file as a unit of storage. A file is a sequence of bytes, and users own files and they read-write files, and we need to set up permissions for individual users to these files. Moreover, file systems need to be robust to machine failures. There are a lot of intermittent things that can happen, or even things like a power failure. In such case, when the system boots up again, the file system needs to be in a consistent snapshot state so that the system can boot up. If the file system is inconsistent, then the system has to go through further checks. So what if a file was written halfway through, for example? So what is a file? A file, this is a very abstract definition, and it's purposefully abstract because a file can mean a lot of different things. And so, like, for example, a file could be storing a graph, it could be storing records, or it could be just a sequence of bytes, like a media file. So a file is an abstraction that the programmer sees to store information. It's a logical unit of information created by a process, and it has a name. And it has other forms of information associated with it, but the primary thing is that it's got a name and it stores some information. And it has other things such as information about the ownership, permissions, so on and so forth. An important characteristic of files, compared to all other abstractions we've seen till now, is that they're persistent. They exist regardless of the processes that are using it. In fact, they're shareable between processes. They come into existence when a process creates them. And even if a process dies, they just continue to exist so that they can be accessed by other processes. And they have a consistent and clearly defined structure on how they are stored. So it's important that the OS manages these files. File naming rules are dependent on the operating system. There are certain characters that could be legal or illegal, such as spaces. The named characters could be case sensitive. For example, Mac OS does not distinguish between lower and upper case, while Linux does. And they also may have certain specific structures, such as extensions. Examples of file structures include, like I said earlier, there could be a byte sequence, like in the first example. They could have records in them. The disk itself does not understand these. These are subject to the higher level abstractions that the programmer perceives. And so file systems could be storing information about the structure. And they could also be storing things like trees. There are typically 2 or 3 types of file types. So the first type is just regular files, which are either text files or binary files. Most of your core text files are all specifically readable by certain editors. And binary streams are essentially have specific meaning. That is, they carry code that can be run on the system. Directories essentially, as we'll see, are a representation, or they're a structure in the file system that essentially helps you organize files. And their implementation essentially is such that directories themselves are just files. They are files describing the relation between the directory and other files inside the directory. Finally, file abstractions are also useful, are a universal abstraction that are useful for accessing I/O devices. So if you have things like a display driver, or even like a disk, or different types of disks, such as USB and so on, or flash, or your standard conventional hard disk. In all such cases, because the programmer is very familiar with the file-like interface, exposing such an interfaces helps them build other things on top of the system. So anything under /dev are all devices that are really exposing a file-like interface to the programmer. File accesses is dependent on the program entirely, but typically they either tend to be sequential or random. And as we know, sequential access are have much better performance with disks, while random accesses don't. And this becomes important since files expose a certain abstraction, it becomes important as to how you lay out the file on the disk based on the access pattern. And so it's up to the file system to map specific portions of the file or the blocks in a file that the user thinks is just sequential or has some structure onto the disk. And how that mapping happens has a fundamental direct impact on performance. If the mapping matches the access pattern and is all sequential, then you're going to get good performance. If not, then the performance is going to be bad. Here are examples of file attributes. So certain file attributes could include things on protection and access control. Certain of flags enable things like locks, which control how many threads can access the file at the same time. They indicate whether system access or whether the file is there for archival purposes. The hash stuff, which talks about records and key length, are specific to databases. File systems could include more information such that they are specific to the application that's running on them. And they also include things like timestamps, which are used for versioning. And here's an example of where files are much more richer abstraction. For example, things like SVN or Git or any of these versioning schemes need to have some notion of when the file was last modified. And so in such cases, the timestamp becomes extremely important and files include that information. And finally, they include size, which is a preliminary check to indicate if two files are the same or equal. A directory is just a collection of files and or other directories. Typically, it's a hierarchy, but not necessarily always. For example, in the case I've shown you an example of Unix, where if you have links, then you could have backward links to folders from where you, from whom you descended, and you achieve this essentially to. So you do this first of all to enable shortcuts to be able to access different folders and files rapidly in the naming structure. And you achieve this using things known as hard links and soft links. Hard links essentially are essentially have multiple directory entries pointing at the same file. So if you modify one of the entries, then you modify the file itself. If you delete one of the entries, you delete the file as well. Soft links, on the other hand, behave as shortcuts. So essentially, you could have multiple references pointing to the same file. If one of them modifies, then it modifies. But you could delete one of the soft links while leaving the file in place or without touching the other soft links. And name resolution is the process of converting a logical name into a physical resource such as a file. So you traverse successions of directories until you reach the target file. And we'll see that a little later as to how you actually perform name resolution. Path names essentially are the way you refer to files. So there are two types of path names, absolute and relative. Absolute specifies everything from the root directory. So it includes a path separator, which depends on the system, whether it's a forward or a backward slash. Typically, it's just one of these two characters. And then you include folders names, in this case, user, friend, mailbox. So you include these as part of the path name. Relative path names do not need to use the absolute term, but simply specify relative to the current directory using the following notion. So you use a dot to indicate the current working directory. And the current working directory can also be obtained by the CWD variable. So in such cases, the system automatically prefixes our search is starting from the current directory. It just assumes that our search is only starting from the current directory. And directory operations are similar to file operations. They include create, link, and unlink. There are multiple components to the file system. First, there's the disk management, which talks about arranging a collection of disk blocks into files. We'll look at this in detail and look at how we map. Like I said, it has specific impact on performance, but it also has impact on how fast we can grow and shrink files. So it has to be adaptable, but at the same time ensure high performance. Naming, which tries to locate a file, and the user provides to the file system so that the file can be tracked down. So naming has a whole separate metadata structure on its own in order to help the user track down these files. Then there's access security, which we looked at a little while ago, where you have users accessing the same file and you need permissions on them. And finally, in the next segment, we'll be looking at reliability and durability. So reliability and durability refer to what happens when the system crashes. What are we guaranteed? The access to a file is controlled through what's known as a file descriptor. So this is your gate. So anytime you want to access a file, you got to create a file descriptor for the file using the following open call. So when you do an open, what happens is a unique integer is assigned by the operating system to the file and is returned in your descriptor. So with the specific read or read-write permissions. And the user process uses this file descriptor for all subsequent accesses. This is so that you don't, it simplifies the interface. For one, you don't think about what would happen if you had to pass, every read and write, you had to pass a character stream referring to the file name. This is going to be quite expensive because you got to set up a buffer, copy the name into that buffer, and then the kernel will have to copy it and then parse a string, right? Except if you have an integer, it's very easy, just pass it through a register. Because integers are fundamental types, it's a lot easier to deal with these, and it also allows the operating system to index into this file or refer to this file throughout its access phase using the descriptor. And so this descriptor is unique to every open file in the system. And so if another process also wants a descriptor for the same file and tries to open it, the same descriptor would be returned. And file systems maintain an internal data structure for each open file, for each valid descriptor. And with each process, you have a system-wide list. You have a system-wide list of descriptors, but with each process, you also have a whole bunch of descriptors which are destroyed when the process dies. So here's an example of how a block would be read. So first you open the file table and you create the file descriptor. So you open the file and that's returned to you. And then when you do a read, the read call gets passed into the system and is translated. The user buffer and size that needs to be referenced in the file is translated into a physical block and size and device parameter by the translation device driver layer. So by the disk translator. Once that happens, the data gets accessed and thrown into a buffer cache. We look at this more in detail. This is in memory, so it caches all the data that the file that is accessed from the file. This is so that subsequent access to the file can be fast and need not go to disk, or if multiple people try to access the same file, it's also fast. And finally, the data is copied from the buffer cache into user space. The disk is typically divided into several partitions, as we saw earlier, to help with search and seeking. So each partition consists of a boot block, which indicates if the data needs, if there's an operating system residing in the partition that needs to be booted. The first few blocks or sectors of the disk are written with this thing known as an MBR, which stands for Master Boot Record, which contains information about the partition table itself as to where the starting and ending of each partition is. The boot block, following the boot block, there's also a super block, free space management, and inodes. We'll look at each of these parameters in detail, but just to give you an idea, all of this has to do with managing space. So it's all about the disk, the partition having a certain amount of space, and as you're creating these files have to be mapped into sectors in the space. And the question is, how do you maintain the free list of blocks? How do you allocate them to files, and how do you manage them? So the key issue with implementing files is, how do you keep track of which disk sectors a file goes to? Okay, there are many different techniques. So for example, if you have a block size of 5 kilobytes and you have a file of 2 kilobytes almost, you need 4 blocks on the disk. The question is where you're going to get these 4 blocks from. You could either do continuous allocation, you could get it from different places, and all of these each one has its own pros and cons, and we'll try to look at what Unix does and what Windows does, the basic design. We'll try to understand the trade-offs. So the big challenges with file system implementation is that one, files grow and shrink in pieces. So they may grow in the middle. So you may have a file that wants to expand at this point. It may want to extend at this point, at the ends. Lots of different places it may want to expand at. And so the question is, how do you do that? A little knowledge about the access pattern would also help, because then you can take particular care to lay out the sectors in a sequential fashion that are accessed. Files also tend to be of different sizes, going all the way from a few bytes to a few terabytes, which means that Uh, the allocation policies would also need to change. The allocation policy that you use for small files will be very different from large files, because with small files you don't really care about expansion and they're pretty small, so you just allocate continuously. But with large files it may not be possible to find such large continuous chunks, which means you need to use some kind of linked list allocation, which has its own pros and cons. And there's a constant desire for efficiency and goal to mask disk latency. And so that is a big challenge, and most of what file system allocators do is try to deal with that. So the first one we're going to be looking at is continuous allocation. So this is one. So this is the first type of allocation policy. So in this one, what we're going to be doing is looking at how files are allocated in a continuous chunk. So we've got files A to F, and we see that each of them reside in a continuous block in the system. This is great because you can easily specify the start and end addresses, and you don't need to have any fancy metadata structure to track where the blocks of a file map to sectors on the disk. The challenge though is when you could have free chunks. For example, you can't have a 7-block chunk fitted into this even though you have 11 blocks free. Continuous allocation is similar to segments in VM, in the sense that they try to allocate continuous data, which is not really feasible, and so they would have to deal with fragmentation issues. So there are two types of fragmentation issues they have to deal with. Internal fragmentation, where if the block size is too big, then if the file is too small, then you waste all this white space. And you also have external fragmentation, where free blocks are scattered throughout the disk. And the big challenge with continuous allocation is that growing a file is a really hard task, because you have to find, essentially wipe out the file and find another continuous block. And finding that could possibly mean relaying or other files in the system, and it's just a hard bin packing problem. So the pros are simple to implement, not too much metadata needed. Read performance is excellent because all the data is continuous. The cons are it's expensive to grow a file since relocation is necessary, and possibly you may need to relocate all the files as well. And the deletion of files may cause external fragmentation. An alternative to the obvious continuous array-based allocation is linked list. In this case, you have metadata where what you have is that you have the file block itself, and then you have a pointer to the next file. So in this case, physical block 4 has the file block 0, and it also includes a pointer to point to physical block 7, which includes file block 1, and so on and so forth. So you essentially create a linked list of this blob where we include the file block and a pointer to the next physical sector that's holding the file block. And so the pluses are it's easy to create, grow, and shrink the files, so there is no external fragmentation. The minuses are it's impossible to do true random access. For example, if you want to get to this one, you'll have to follow 5 pointers to get here, right? And so as you go lower down on the file, and if you go backward, it's very hard to do random access. And it's also a big challenge for reliability, because if you break one of these links, then the rest of the file is kind of hosed. So remember that the pluses with this, it's easy to create, grow, and shrink files, because we're going to use this property as we go along. So the big pros for linked list are no spaces lost due to fragmentation. File is still referenced by a single pointer to its first block, so you don't need to keep track of all the blocks in the file. And sequential access of the file is efficient because all you got to do is follow the pointers once in a while. Random access of the file is not efficient, while with the continuous allocation it would be. And furthermore, this is a more subtle challenge in the sense that note that you had a small pointer at the top of the data block. The challenge with this is typical sector sizes tend to be 512 bytes. Now we are adding like a 4-byte chunk right on top of the 512 bytes. And this is challenging because where are you going to get the space from? It's no longer powers of 2, the block itself. It's a weird number, and so allocating such a block becomes a challenge. So Windows took this is the approach that the earlier Windows systems took, which is called FAT, or File Allocation Table. So what they do is they take all the linked lists and then move them to a separate metadata structure. So in this case, they would take all these pointers and co-locate them on a separate table, so that you first of all you make the sectors once more uniform in size, and that's a big advantage. And also, because all the pointers are located together, it can support better random access performance. So we'll look at why that's the case in a second. But the general idea is that the FAT table is significantly smaller than the blocks themselves. So it's possible to hold it all in memory and then achieve better random access properties. So if you think about how much memory is needed for this table of pointers which need to be in memory, it's quite significant. And that is the big challenge with this system. So if you have 400 gigabytes of disk, 4 kilobytes per block, that's 100 million blocks. So the FAT entry needs to have 100 million entries. And this, if each one is a pointer, this corresponds to approximately 400 megs. So one possible solution to this is you use larger clusters of storage space, but this obviously leads to internal fragmentation, or you could allocate different parts of the file next to each other, leading to better locality properties. So FAT, while it has the inherent disadvantages, it can be tuned to possibly eliminate that, or possibly reduce the effects of some of them. So in this case, the size of the FAT table is directly proportionate to the size of the disk. Okay, so note that we're moving away from the file abstraction in this case. In this case, what we're saying is that the size of the table is proportional to the size of the disk. Something like reverse index page tables in virtual memory. So each entry contains the block number for that corresponding to that file, and also a pointer to the next block. So file A starts at this block, and it contains a pointer to the next one, right? So in this case, 7 points. Right. So in this case, 7 points to 2, 2 points to 10, 10 points to 12. 12 is -1, indicating a termination in the files. The big pros for FAT are there are no pointers in the data blocks. Data blocks are all uniform in size. Random access is easy since the pointer chasing is done on the table, which is in memory, which supports random access. No need to access the disk blocks themselves. The cons is that the entire table must be kept in memory, and it can get large. So let's look at what UNIX does now. So UNIX adopts a slightly different methodology where it directly improves on the pointer-based structure. So the first thing is it takes all the pointers that correspond to the file and then move it into a separate table. So there's one inode per file. Okay, so that's the root inode. Okay, so this is not proportional to disk anymore. The number of pointers in this is proportionate to what the file size is. The bigger benefit is that such inodes need to come into existence only when the file is open. Until the file is open, such inodes can exist on the disk. So the amount of memory occupied by the file system is directly proportional to the number of file inodes, which is directly proportional to the number of files open that are being accessed at the same concurrently. So if you do not access all the files at the same time, this is beneficial because then you don't need to allocate all the inodes, which means all such nodes can exist on the disk. So it ensures that files which are idle or not accessed do not consume any memory space. That's the biggest difference with respect to FAT. With FAT, all the inodes or the pointers have to exist in memory because there's one for each disk entry, list sector. So the pluses with the linked list, obviously it extends, it's easy to grow and shrink. There's little fragmentation, supports direct access. The minuses is that the question is how big is this inode itself? It's a specific challenge, right? And how to handle large files. So the problem with the inodes is that, let's say that a certain file is 4 kilobytes and you had let's say 1 kilobyte sectors. The 4 kilobyte file would need only 4 pointers, right? But the 8 kilobyte file may need 8 pointers, right? And let's say, and one of the things we mentioned earlier on was that files in a system tend to vary a lot in their size. So you can go all the way from to a few kilobytes to a terabyte or to hundreds of gigabytes. In such cases, the inodes for each of these files are going to be dramatically different, the space requirements for the inode itself. So the question is, how do you build variable size inodes, or do you even do that? So the way to deal with this, and Unix adopts a systematic methodology to essentially optimize both the small and large files. Essentially by saying that, the way large files can be dealt with is by creating an index block. So you have an inode pointing to an index block that further points to the data blocks themselves. Right? And this is a one-level organization. And so in this, it holds the pluses from the previous design, but it can still support large files because you can have as many index blocks as you want. And the only overhead is, what's the overhead of creating small files, right? Because small files, if a file is only one block and you need an index block and an index, each of them which themselves are a block, then you need at least 3 blocks for a file where the data is only 1 block in size. And so that's not very optimal. And so that's a big challenge with these systems. But essentially they are composable, which means you can go multiple levels. So in this case, I'm having a 2-level indirection. In this case, I'm having 1, 2. The index blocks themselves could point to other index blocks which point to data. Right? And so in such cases, it's possible to compose and create multi-level index blocks. So what are these inodes or index blocks, right? So an inode is essentially a disk address of file blocks plus a pointer to another block which itself may contain another set of disk addresses to file blocks. So it points to data and it points to metadata which might point to data. Right. So it may point, so inode can be recursive, it can point to data or it can point to other inodes themselves. So what Unix does is multi-level indirection. The file header contains 13 pointers. 10 point to the data blocks, the 11th points to one level of indirection, the 12th points to doubly level of indirection, and 13th points to a triple level of indirection. So you can see the reason for the following. For one, this allows transparent expansion from small to big files. If you have a file that fits within 10 blocks, then you don't have any pointer indirection at all whatsoever, because you have one level of index block that can store all the 10 pointers. And the 11th, which the indirect block, is null, and all the other pointers are just null. So it directly points to the data blocks, right? If you have one that's 11 blocks, then you need one level of indirection, okay? And so the upper limit on the file size is how deep can you go with the hierarchy and how many pointers you have per index block. And if you do the math, if you have a 3-level hierarchy like a triply indirected block, and each one of these blocks contain 10 pointers, then that's 2 to the 30. It's approximately 2 terabytes. So the features are that it's simple, files can easily expand, and small files are cheap. And the cons is that large files require a lot of indirect indexing in order to get to the data. So compared to FAT, if you had a large file, then you'd have to follow multiple levels of pointers to get to the data itself. So here's an illustration of the UNIX system. So if you have the inodes, the first 10 blocks directly point to the data. The first level of indirection, and then you point to, again, 10 data blocks again. This itself does not point to any more data blocks. Then you got the second level of indirection, which itself could point to another set of index blocks, and they could point to data. So in this case, the second level of indirection, each of these points to 10 index blocks, each of which could point to 10 data blocks. And then you've got the third level of indirection, which is, you point to a second level of indirection, then that could point to index blocks, so on and so forth. So by the third level of indirection, you're accessing n-cubed data blocks. The pros with the inodes are that, first of all, it's small in size. Like I said, only the inodes or open files needs to be in memory. In contrast, the fat table size is directly proportional to the total number of disk blocks. And so this allows adaptive systems where the file system can support a few large media files, or can support a whole bunch of small configuration files, or something in between, or if you have both of these files in the same system. The cons is each inode has a fixed number of disk addresses. A file may grow beyond the limit. In such cases, you would have to reserve space and then point to another set of disk block addresses. And there's also the cost of indirection itself to get to the data when the file starts growing bigger. So now let's look at implementing directories and naming. So a directory system essentially maps a ASCII file name to the information needed to locate the data. So the question is, where are the attributes for the directory itself stored? For example, a description of what files are cached underneath it. So in the case of Unix, it's essentially a reference pointer where you store the directory names, and then each of these contains a pointer to an inode that contains the actual description. And this is so that it maintains an abstraction for directory that is similar to files. So directory ends up looking just like another file. On the other hand, Windows similar to FAT, stores the attributes along with the directory name itself. And so if you wanted to locate a certain file or folder with a specific name, this involves parsing multiple levels of directory files, following their inodes, and then checking, essentially doing a string matching on each of those inodes. An interesting issue that occurs with files is choosing a block size. Large block size means internal fragmentation could occur, decreased disk space utilization, and wasted space. Small block size means most files occupy multiple blocks, thus you need multiple seeks and lookups on the disk to get to the data, and this results in reduced performance. So there is no one size fits all. It also has critical impact on how the free list is maintained. So the free list needs to keep track of which data blocks are free. Remember that when you map a file to the disk and create space for it, you need to keep track of which blocks in the disk are free so that you can allocate. So there are two ways of keeping this list. You can either use a linked list or a bitmap with a flag, a 1-bit flag indicating whether the block is free or not. We'll look at the trade-offs in each. With the linked list, as the number of free blocks reduce in the system as you're going along, its overhead is directly proportionate to the number of free blocks. And as the number of free blocks shrink, the overhead for the free list shrinks. With the bitmap, it's fixed overhead. A disk with n block always requires n bits. So you can imagine 100 million entries, right? So they require 100 megabits. And that's quite a lot of space. And as the file system starts to fill up, the overhead for the free list does not reduce. For example, all of these would turn to ones, all the zeros would turn to 1, but the free list overhead would still exist unless you apply things like compression. So with the bitmap, the amount of space required is directly proportional to the number of blocks. So if you had an 8 GB disk with 2 kilobyte blocks, that's 250 disk blocks, which corresponds to about half a meg. So an interesting question is, when will the linked list scheme require less space than the bitmap scheme? And the answer is that when the disk is nearly full. The final issue that we got to look at is file system caching. So files exist on disks, and it's inefficient if you keep going to the disk all the time for multiple reads to the same file. So what OS has maintained is something known as buffer cache in order to hold the data in memory. And so the key idea is to exploit locality by caching the data in memory. And so the buffer cache itself uses memory and acts as the memory it's used to cache kernel resources, including disk blocks, which is the metadata associated with the file, the name translations, and the data itself. Since it's a cache, an important question is what kind of replacement policy we've got to employ for it. Um, Systems normally employ LRU. This works reasonably well for name translation. It works reasonably okay as long as you have enough memory allocated to the buffer cache. It does not work well if you start scanning through the file, because remember that with LRU, it depends on reuse. You need to have reuse for LRU to work. In fact, it works pretty badly if all you're doing is just streaming through the data. In general, it's a hard problem to optimize, so most systems allow you to choose some kind of policy. And people who build large systems like databases do take advantage of the buffer cache. It's extremely important for performance purposes. Another question is how much memory should the OS allocate to the buffer cache versus virtual memory? Remember that the buffer cache and virtual memory are both resident in DRAM, which is a finite amount of resource. The question is, if you have too much memory for the buffer cache, then you can't run many applications at once because applications need virtual memory, right? And if you have too little memory for the buffer cache, then many applications may run just slowly, and disk caching is not effective. An important optimization is how do you adjust the boundaries dynamically. So a final issue that we're going to consider is prefetching, which is essentially used to exploit the fact that common file accesses are sequential, but they're first-time accesses, and we have no idea. They do not have a chance to be in the buffer cache before they can be read again. So with prefetching, the big question is how much to prefetch, right? If you have too many, then you impose delays on the request by other applications. If you have too few, then this causes many seeks among concurrent file requests. And because it's a cache, writes to files are not immediately sent out to the disk. So it's similar to a write-back cache in some ways, because the disk latency is so high, you don't want to deal with it. So essentially, the presence of the buffer cache can leave unwritten file blocks in the cache for a while. So a challenge with this is what happens if the system crashes before the directory file has been written out. You lose a pointer inode, what data that you just stored does not exist anymore. And another challenge is what if some other application tries to read the data before it's written to the disk. The former is, this challenge is not so particular because you can solve it with bypassing, which is essentially every read also checks the buffer cache and checks if the data needs to be sent back from it. The solution to this challenge of the file system crash is essentially to flush the buffer cache to the disk periodically. Typically in Unix, it's every 30 seconds. And so the disk scheduler the advantage with delaying this flushback is the one, the disk scheduler can effectively reorder a bunch of requests, or you can filter them out if you write the same file multiple times in 30 seconds. And the other benefit is that some files may never get written to the disk. For example, you have temporary files created and deleted quickly, and in such cases, they'll never be flushed to disk. But the disadvantage is what happens if the system crashes before the file has been written out, and how do we recover from that?